smooth. And hence many things can be said, many more can be said in this case, some kind of finiteness type of statements. But for P2 it's a P is always. We just completed last possible case of singular points. So now it's a theorem for Lagrangian fibration over P2, but I think it can be also said, the same thing can be said for V3P. So the argument is quite general. So. Okay, sorry for making it. I just wanted at least to reach the point. The point of the first lecture I will give you in the short. Okay, maybe you have questions, because I think in the meantime, yeah, okay, go.
Thank you very much. Questions?
Okay,
So to construct to construct singular Lagrangian fibration hyperkahler manifold, is it enough just to find is the goal to find abelian variety which is inside, and then we'll
yeah, if you have a one abelian variety inside, basically smooth abelian variety, this trivial Norman bond, and so an abelian variety which is isotropic, isotropic with respect to Lagrangian abelian variety. Then you can, but by now, that's a question.
There's one fiber, right?
One fiber. Yeah,
then
then deformations, then you can deal. Well, I wouldn't say 100%, but basically that's what people.
How do you make this global?
Yeah, and then it globalizes. Basically, normal bond has to be trivial, and then you can deal with it. So it's possible. But one fiber like that would be sufficient, and it's still not there.
Can some quotient of abelian variety, quotient of torus appear as fibers, or they always
usually not, they're multiple. The multiple shouldn't appear. So if you have a multiple fiber, then there is something in projective case. Okay. You have a look at projective case only.
So there's kind of, if it's a Lagrangian fibration, then it has to be generic fiber has to be.
Generic fiber has to be trivial. Yeah. No, but it is because how to say the bond is trivial downstairs. The bond has to be trivial upstairs. So no kind of you have no automorphism. So it's all reduces to one simple question. At least for one of these infinite number kind of everywhere dense of devices, potential devices, find one where in fact you can say that this is.
But why should you have a torus? You can have a three-manifold. You can have a three-manifold, oriented three-manifold vibration.
No,
it has a trivial norm.
No, it's a torus because it's Lagrangian. It's Liouville type.
But the three-manifold can be Lagrangian six-manifold.
Sorry?
Because it's trivial.
No, nothing like that happens. If you have, so suppose you have something like a K3 product by torus, yes? Then it is a direct product of K3 by F. So essentially K3 cannot change because you have the form has to be the same, and you have direct. Now everything is concentrated at exactly one point, getting a torus inside, getting this kind of flat torus, flat isotropic torus of codimensional. That would be it.
What do you expect out of the base?
Out of the base, it's expected to be PN, projective space.
Just projective space.
Yes, and I think it's kind of very close because this similar statements can be proved for. I think codimension 2, extracting, getting rid of codimension 2 should follow just the same line as in our paper or in the paper of Hilbert. So just a little bit more. And if we get rid of codimension 2, I believe there is no other synchronous. And in fact, it's hidden, but I think it's hidden in Huang paper and in Huang and Matsushita, but they just didn't pursue it.
Is there any kind of complex version of SYZ, like hyperkahler with this fibration gets a mirror complex?
Yeah,
mirror
there is this mirror. Oh, mirror story is there. Yeah. No, but it is the beginning. Mirror story is.
But I mean, complex mirror. Right? I mean, this SYZ mirror symmetry is the real torus fibration, Now it's kind of complex torus fibration. Is there some complex mirror?
Yeah, it's the same kind of metric duality. I think usual SYZ you have a metric duality, you do torus, and here is the same story. I think there is a lot of mirror case 3 is. It's much simpler in a way, but there is some mirror symmetry for case 3. So I'm sorry, because since each deviation I was pushed in is a huge subject. So even to say something about it takes, to say something sensible takes a lot of time. So it's a vast area by now. It's surprisingly vast. It's surprisingly few objects.
I also have a question. So this Verbitsky theorem is a kind of global terrain, right?
Yeah.
So is there some natural marking, as is in the case of K3, to get injectivity?
Well, if you have so now if you take projective injectivity of
Well, in the case of K3, you consider marked K3, and then
but
so the statement is that the map is injective from
you see marked. Let's say it's always a marked is injective. Marked is a greater element H2, H1. So for example, if you have again modulo this non-Hausdorff, there are non-Hausdorff points. So points about which you have several models. Yeah? Several varieties, finite number, but several different varieties. Marking here means usually giving an element in H2, saying, okay, this element is going to be positive, ample, and this is polarization. So marking basically you can say about marking in projective. And in Kahler case also you can say, okay, this is this class you want to have as a Kahler representing Kahler metric. Then with that you have similar modulo again, this non-Hausdorff examples. Yeah, it's but again it is a finite number because it may happen that the map of the model is actually finite too. So the theorem tells you about the existence of something which maps finitely. And I think there are examples when it happens.
But can it go that within the same birational class you have several projective models, but the polarizations are in separate?
Yeah, in several, how to say, as usual.
And polarization, do they have
Several
to be
cameras,
number
yeah, several
or-
cameras, yes. Yeah, it's usual thing. It's also. Frank also in the wrote a chapter in 73 about all these cameras and so on, but I couldn't imagine that conjecture. I would say the point is that if you have varieties with trivial canonical class, then have the same cone of effective devices. Devices move to devices. That's the point. If you move from variety, if you have birational transformation of variety of trivial canonical class, then devices move to devices. So therefore effective devices are effective devices. But there are cameras. So it's all split cameras. It's not completely. So for one camera this is positive, for another this is ample, for another camera this one and so on.
So all bad things happen.
Sorry?
All bad things happen.
Yeah. It's not very bad. You have the whole structure.
Okay, if there are no other questions, let's thank Fedor for